Solving exponential and logarithmic equations now. This is one of the reasons why you had to learn all those properties of logarithms last time. So a couple principles to keep in mind. If you have two exponential functions equal to each other and their bases are the same, then their exponents have to be the same. The same thing if you have two log functions equal to each other. If their bases are the same, then the only way these are going to be equal is if their inputs, the x and y, are the same. And this will be for bases greater than 0 and not equal to 1. So a couple strategies you can employ with exponential equations. If you have two exponential functions equal to each other and the bases are the same, simply set the exponents equal to each other and solve. Or if we have an exponential function equal to a constant, we can take the log of both sides, and just for convenience I'm using the natural log. The common log would work just as well, or any other log base. Once we take the log of both sides, that allows us to get at the exponent, pull it out in front, and now becomes a multiplication problem. And then we can divide both sides by the natural log of, got a typo in there, the natural log of b, and x equals the natural log of y divided by the natural log of b, and solve from there. Now for log equations, two strategies we use the most is if the two log functions are equal to each other, the bases are the same, then the inputs, the interior functions here, have to equal each other. Or if we have a log function equal to a constant, rewriting an exponential form allows us to get at the input here, and then we can usually solve from there. And just a reminder to watch out for extraneous solutions. Okay, our first example is a pretty easy one. We've got 3 to the x subtract 4 equals 27, and 27 can easily be written as a power of 3 cubed. So since the bases of the exponents are the same, we can simply set the exponents equal to each other and solve for x. And then this is a very easy one to check in the original problem. The next example is a little more complicated, but notice it's very similar to the last one, except we're equal to 26 instead of 27, so our solution should be very close to 7, the solution to the previous problem. This one, what we'll do is take the natural log of both sides. Again, I just picked the natural log for convenience. That allows me to grab the exponent, the x subtract 4, and pull it out in front here. Then I can divide both sides by the natural log of 3, isolating my x subtract 4, and then by adding 4 to both sides, I get my solution. So this is what we call the form of the exact solution, and then this is the approximate solution. And on your test, I'm going to be looking for both of those solutions. This one's more accurate, this one's more useful. And here's a second way to solve the same problem. Some students prefer this. Most students seem to prefer this one, this method originally. So this one, what I'm going to do is rewrite it from exponential form into log form. So the base of the exponent swings around, becomes the base of the log. X subtract 4 is log base 3 of 26, and then add the 4, and that gives me the exact solution. To find the approximate solution, I'd use my change of base formula, which would give me this, and then my approximate solution. So both of these exact solutions are equivalent. This one's harder. The bases are not the same. We've got 3 to the x plus 4 and 5 to the x. So the only way to get at this one is to take the natural log of both sides, pull the exponents out in front using our properties of logarithms. And just a note here, most students look at this and you get really intimidated, but remember the natural log of 3 and the natural log of 5 are just numbers. Algebraically, this problem here is equivalent to solving this problem here. X plus 4 times a number equals x times a number. I know you know how to solve this one, so we can solve this one. Just keep reminding yourself the natural log of 5 is just a number, the natural log of 3 is just a number. And you could approximate those numbers on your calculator just to remind yourself of that. So what I'd do here is distribute, and then I want to get both my terms that have x's on the same side, so subtracting this over. And then because I can't easily combine these, even though they're like terms, what I did instead was factored out the x. And again, natural log of 5 subtract the natural log of 3 is just a number. You could approximate it with your calculator. We can divide both sides by that number, and then I get the exact solution for x. And the decimal approximation is 8.603, and easy to plug that in and check. Now when I do the check, the answers look like the difference of 200, but if you're talking about $1 million, are you going to worry too much about $200? If we carried this more decimal places, this would be more accurate. Okay, I had a brief interruption there. So I think we're almost through this problem. Dividing, we can isolate the x, get the decimal approximation, plug it back in, do the check. And that's what we were talking about. Okay, so the check doesn't look like these are exactly equal to each other. That's because of rounding error. If we carried this out more than 3 decimal places, this would have been more accurate. Okay, looking at a log function here, easiest thing to do with this one, because it's a log equal to a constant, is just switch it from the log form into the exponential form. The natural log is log base e, so I went ahead and wrote the understood e in here, rewrote it. E to the fifth is just a number. Subtract 2, divide by 3. We get our exact answer, and then our decimal approximation. And this one's pretty easy to check on our calculator because we've got a natural log function programmed into it. This one's a little more difficult because we've got two logs equal to a constant, but we can use the properties of logs to combine them so that we have a single log. And once subtraction becomes division, once it's a single log equal to a constant, we write it in exponential form. We've got 4 cubed, which is just 64, and we've got a rational equation to solve, just like back in Math 95, and we did some of these in Chapter 1 also. Multiply both sides by 2x, include the fractions, gather the like terms, solve, and get our solution. Okay, one more of those. This one also, we have a log plus a log, so we can combine those into a single logarithm. In this case, will become multiplication using our properties of log. Then once we have a single log function equal to a constant, rewrite in exponential form. And this one's going to turn into a quadratic equation. So put it in standard form, set it equal to 0. It factors. We get two solutions, positive 9 and negative 1. But remember about extraneous solution. The domain of the log function is positive values, so x cannot equal negative 1. So we'd be taking the log of a negative number, which is not defined, and so our one solution is x equals positive 9.